Okay, I want to talk about problem 6.64. 6.64. This is kind of a tricky one. What I'm asking you to do in this problem is to do a little bit of mathematics, and so some of you are gonna struggle at this, and I hope that you took it upon yourself to explore maybe your calculus text or check back with your notes. But I want to talk about this problem because it's kind of an interesting one. So we're told that the force in the x direction on an object is some constant f0 e to the minus t over big T, capital T, which is just some time. Okay. So the first thing that we might be thinking about this is, oh, this is an exponential. It's going to blow up. The force is going to get huge. Well, one of the things that I encourage you to do is when you encounter a function or anything that you're not sure about what it looks like, is to try to find a way to plot it out. Okay, so I'm going to plot fx as a function of time here, and you can plug it into Excel. That's a really good way to do. Pick some time t, pick some constant t, and just plug it in. Just pick some constant, pick some f0 or call it 1, and then look at what happens, because unlike what you might be thinking, fx kind of looks like this. It starts at some value, f0, so e to the minus, this is an e to the minus 0 is 1. So it starts at some constant, and in fact, as time evolves, it decays exponentially. And in fact, when we reach some time t, it's decayed to about 37% or 0.37 of the initial value. So that's just a property of the exponential. Now in this problem, we're asked about the velocity and what it does as a function of time. Okay. So first of all, we have to do a little bit of calculus here. And the first thing that I'm going to do is I'm going to employ Newton's second law. F net is equal to ma. And in the x direction, we have one force, F0, e to the minus t over big T. And that's m, a. But the acceleration is m dv. I'm sorry, the acceleration is the derivative of the velocity with respect to time. And so I'm going to rearrange this thing. I'm going to bring the t to the other side, bring the m to the other side, and just rearrange it a little bit here. So dv is then going to be f0 over m. And I'm going to get my term here, e to the minus little t over big T, and then the dt comes out here. Okay, so this is a differential equation, and we actually have to integrate it, but it's okay because it's separable. So I'm going to integrate both sides, and I'm going to integrate from the velocity from where I begin to some velocity as a function of time. And I'm going to integrate this side from t0, where I begin, to some final time later. Okay. What I did is I just put primes in all of my variables because they're dummy variables. I integrate over them. Okay. So for those of you that remember, the integral of dv is just v. Okay. So I get v prime, and I evaluate it from my lower limit to my upper limit. And that equals to this thing. Well, I have a constant, f0 over m. I have the integral from t0 to t of e to the minus t over big T dt. And you have to dig deep for this one. I think if you don't remember exactly how to do these integrals or find these antiderivatives. Basically, this thing, I want to evaluate something that when I take the derivative of it, I get back the original function. So the antiderivative is, well, when I take the derivative of it, I get what's inside of here. I get this thing. And I think